All right, guys, this is our last lesson on area and volume. This is going to be about doing areas and volumes along the y-axis instead of the x-axis. So a lot of the same things will remain true, but it's going to be a new technique that allows us to solve more types of problems. So let's start with a warm-up. That's stuff you should already be able to do. Let R be the region enclosed by f of x. The horizontal line y equals 4, as shown in the figure above. This is something you should already be able to do. Find the volume of the solid generated when R is revolved around the line y equals -2. So here is the line y equals -2. If we are revolving it around, this is our center of rotation. And so we're going to end up with like these circles here. Now we'll notice there's a blank space between where the region starts and here. And so this is going to be, for A, this is going to be one of those pi big R squared minus pi little R squared ones. So this is going to be the integral of the area at each x. And the integral is going to go from here to here. We need to find where this is. So let's start by, in our calculator, putting in y equals x to the 4th minus 2.3 x to the 3rd plus 4. And we're going to put in y equals 4. And find the intersection to see where that is. I guess I should actually change my window a little bit. So let's go -2 to, I don't know, it looks like 5 will be okay. Maybe to 5, because this goes to 4, right? So, okay, so here we go. Let's find that intersection. So second calc, intersect, enter. And on mine, it'll tell you a different thing on your calculator. It says x equals -7.57 e -5. Be really careful with this. This intersection is 0. Like, clearly this is at 0, right? Your calculator sometimes struggles, and that's why we round to 3 decimal places. -7.357 e -5 means times 10 to the -5th. It's 0.000737, and rounded to 3 decimal places, it is 0. The calculator struggles after 3 decimal places sometimes, and that's why we round to 3 decimal places. So this is 0. Don't be fooled by this weird form of writing 0. That's sometimes how the calculator tells you it's 0. So e -5, it's the same as if it was somewhere else. Here, intersect, enter. Let's find our other guess. The other intersection is 2.3, but maybe the calculator would struggle a little bit and say 2.300001, right? And that's still 2.3. It's just like struggling with it. So the integral is going to be from 0 to 2.3. But honestly, if you put in like -0.00007537, like it'd still come out to the same answer. It's still the 3 decimal places, so it'll be fine. And the area here, the area at each x, is going to be pi times big R squared minus pi times little r squared, because this is one of those circles where it's like got a blank center and filled in on the outside. And the big radius is the distance from here, from the center of rotation, to the very outside. So big R is, and we can find that by subtracting the y's. This is y equals 4 minus, this is y equals -2. And so the big radius is 6. The little radius is going to be from the center of rotation to where the blank part ends, so where that region begins. And this y value is based on this curve. So this is f of x minus -2. So r equals f of x plus 2. Now this is fine. Like, I can leave my answer like this because I've said what a of x is. I've clearly labeled it. I've labeled r and said what r was. And so all of this is fine. Like, this is actually fine to get me points. A more common way to write it would be integral from 0 to 2.3 of pi. I'm going to factor out the pi since these both have a pi. We usually factor it outside. Pi times 6 squared minus pi times f of x plus 2 squared. So that's how I'm going to enter it in my calculator. So pi times the integral from 0 to 2.3 of 6 squared minus, I need to open parentheses because this is a binomial, and I'm going to put y1 plus 2 in parentheses squared dx. Make sure this is in parentheses or it'll come out wrong. So 98.868. 98.868. If you put 98.867, that would be okay too. Like if you concatenate, the AP exam will accept that. All right, B. So guys, this gets full credit on the AP exam. So does this if you have this stuff labeled. Without this, this isn't good enough, right? But if you've labeled what A of X is and said what all those R's are, then it's the same thing, right? So that's okay. Okay, B, the region R, so this same region R, is the base of a solid. And now each cross-section perpendicular to the x-axis is an isosceles right triangle with a leg in R. Find the volume of this solid. So you should be able to do this. If this is an isosceles right triangle with a leg in R, then this and this are the same because isosceles means it has the same two legs. This is a right angle. And so we need to find the area at each x. So again, it's going to be the integral from 0 to 2.3. We already found that of A of x. And here, A of x will equal, the area at each x will be 1/2 the base times the height. So this is 1/2. The base is the distance from here to here, so top y minus bottom y, which is f of x. The top y is 4. This is y equals 4. So 4 minus f of x times the height, but the height is the same as the base. So it's 4 minus f of x times 4 minus f of x. And so I'm just going to put that as squared. And again, I've defined A of x here. And so this is good enough for the AP exam. But when I enter in the calculator, I'm going to need to put math 9, the integral from 0 to 2.3 of 1/2. Now, f of x is a binomial, or this area is a binomial. So 4 minus vars y1 squared dx. 3.574 equals 3.574. Again, if you put 3.573, you'd get full credit. All right, last, let's do C. C says, now, the vertical line, x equals k, divides R into two regions with equal areas. Write, but do not solve an equation involving integral expressions that gives the value of k. So I don't know exactly where it is, but maybe somewhere around here. X equals k has to divide it into two equal areas. And so an equation is going to be a relationship between two things, and these equal areas must be the equal sign, right? So it's like area 1 equals area 2. So let's see how we did. This first area, the formula for this area on the left that has to be equal to the area on the right, is going to be the integral from 0 to... we said this is x equal, I don't know why I put x equals 6. This is x equals k. Oh, you guys couldn't see this. Oh, you guys couldn't see this. Oh, no, guys. This vertical line divides this into two equal areas. So here's area 1, and then this part is area 2. And these two need to be equal to each other, and so we can say, like, hey, look, it's going to be area 1 equals area 2. Now, area 1 is going to be the integral from here to x equals k. So the integral from 0 to k of, why did I put area 1 here? This is area 2. Integral from 0 to k of top minus bottom. So 4 minus f of x dx. That needs to be equal to area 2, which is, again, the integral of the top minus the bottom. So the integral from, now it's going to go from k to 2.3. We already found that intersection. The integral from k to 2.3 of 4 minus f of x. And this is it. It said, write, but do not solve an equation involving integrals that gives the value of k. If I were to solve this equation, I would get what k would need to be. But I don't need to solve it, so that's what it is. Okay, so that was a warm-up. That's all the stuff. That's a really good overview of all the different things we should already be able to do. Areas, volumes of rotation, volumes where we know the cross-section or can find a formula for it. And now we're going to get into a place where sometimes it's very hard to find areas of cross-sections perpendicular to the x-axis. So our formula, integral of a of x dx from a to b, won't be very useful because it's really hard to find what this is. But it's really easy to find the volumes when it's perpendicular to the y-axis. So instead of slicing it this way, we're going to start slicing it this way because these will be easy to calculate. And in this case, instead of using v equals the integral from a to b of a of x dx, we'll use the formula v equals the integral from c to d of a of y dy. And the idea is we're going to find the areas at each y and add all those areas up, and it'll give us a volume going this way. Now, when it says dy, this means these are y values. So, oh man, so c and d are going to be y values. So it's going to be like from start, so here's c and here's d, from starting at the bottom of the y-axis to the top, what are those areas? So we're going to add up a bunch of areas, along the way from c to d, and that'll give us a volume. So hopefully that idea at least makes sense. Let's look at an example here. The region bounded by the function y equals x squared. Here's y equals x squared. The y-axis and y equals 4. This area is revolved around the y-axis to create a solid. So it's revolved around the y-axis, not the x-axis. Be careful here. If we revolve this, we're taking this thing and we're revolving it this way now, right? We're revolving it along the y-axis. And so what that's going to end up doing is making a bunch of circles going up. It is incredibly difficult to find the area at each x, but it's really easy to find the area at each y because it's going to make a bunch of circles. Hopefully you can see if you revolve it around the y-axis, it's going to make, circles going this way. It's going to look something like this. It's going to be it's going to look like a cone. Some sort of like revolved cone. Okay. And we want to find the volume. What is the name of that shape? Where it's like this shape? A cylinder. No, it's not a cylinder. What's this called? I don't know. Man, my geometry's weak. I'm forgetting what this is called. It's like a, whatever. Okay, this is the shape it's going to make though. This like kind of vertical shape. So here's what we're going to do. First, we need to find the area at each y. So we need to find a formula for the area at each y. And we know it's going to be circles because it's revolving around the y-axis. It's going to be pi times r squared. There's no blank circles, right? It's just like directly revolved around the y-axis. And so the question is just, what is that r? And if we look closely, we can see that the radius is always going to be this x distance. Right? That's going to be the radius of the circle when it gets revolved around. And so what I can use is I can use this formula and switch it around to solve for what x is equal to find what this x distance. I need to solve for what x is at each y. And so we need to solve what we're always going to do when we're going along the y-axis is we're going to change this to, we're going to take the square root of both sides and get x equals square root of y. I took the square root of both sides. This is a formula for x. And that will be at every y value, the x value will be the square root of whatever y is. If y is x squared, then x will be the square root of y. And that is my radius. The radius of each of these circles will be this x distance. It's the, so this is equal to pi times square root of x squared, which is just pi times x. And that's the area at each y value. Now, I'm going to set up my integral. It's not going to be the integral, let's see. It's not going to be an integral from here to here. It's going along the y-axis. So the lowest y value here is clearly 0, and the highest y value is going to be whenever this region ends. And it told us it was at y equals 4. So y equals 4 is the top y. So we're going from bottom to top instead of from left to right when we're doing these integrals. So it's from 0 to 4, and it's the integral of pi times x. So this is just like, find this integral. This is a power rule. This is a constant. So we're going to raise the power by 1 and divide by the power. So pi over 2x squared from 0 to 4. When we plug in 4, we get 16. 16 divided by 2 is 8, so it's 8 pi. Minus, when we plug in 0, pi over 2 times 0 is 0. So 8 pi. So, this is super easy. The trick is that these are y values. So this is y bottom minus y at the top. And this is now, I guess I should say dy. This is a formula for the x value. Oh my God, guys, I'm so sorry. Oh, this was so confusing. I'm so sorry, guys. This was supposed to be x equals square root of y. Along here, this should have been square root of y squared. It's not going to change our answer, but this should have been pi times y, and this should be pi y times dy. I'm so sorry for that confusion, guys. The radius, this x distance, this r, was square root of y, not square root of x. And so it won't change our answer, like, but that's what's going on. Okay. So I apologize for that. I hope that wasn't confusing. If the region in number 2, so this same region, was revolved around the line x equals -1. And here it should be the area in the first quadrant. I really should have said this is the area in the first quadrant. So again, we've got this y equals x squared guy, y equals 4. We're talking about this region, and it's being revolved around the line x equals -1. We have to be careful. It's not y equals -1. It's x equals -1. And so this is our center of rotation. Then it's going to still make circles, right? But it's going to make a bunch of circles that are going this way. And so it's really hard to find the area at each x. You want to calculate the area at each y because we know how to find the area of a circle, whereas like the other shape it's making going along the x-axis, I have no idea what that is. So this is going to be, again, but here, this region is going to have a blank circle, right? Because we've got a blank space between the center of rotation and where R begins, where that region begins. And so this is going to be one of those ones where it's, again, the integral from 0 to 4. We're talking about dy, right? So along the y-axis, we're going from y equals 0 to y equals 4 of pi times big R squared minus pi times little r squared, just like we did before. And the big radius is from the outside to the center, from the center of rotation to the very outside. And this x distance, again, x is going to equal square root of y. We already found that up above. And so so to find the difference between these, we need to do the x on the right minus the x on the left. So instead of going top minus bottom, it's x on the right minus x on the left. And so the x on the right is square root of y, and the x on the left is -1. All right, this is x is -1. So square root of y minus -1, big R is square root of y plus 1. Okay, the little radius is going to be from here to here. It's the blank part, right? It's from the center of rotation to where it stops being blank. And so this is, again, going to be the x on the right, which is 0. This is x equals 0, minus the x on the left, and this was x equals -1. Guys, this is a little crowded and messy. I apologize. So the little radius is 1. And that should make sense, right? Like, this blank space is always going to have a little radius of 1 because we're rotating around x equals -1, and the region doesn't start until x equals 0. So this is the integral from 0 to 4 of pi times square root of y plus 1 squared minus pi times 1 squared, which is just 1. Go ahead and find this on your own without a calculator. I think you should be able to do it. You really want to simplify this first. So this is going to be the integral of pi. Let's just factor out the pi to the outside. This is a square binomial. We square the first one. Square root of y squared is just y. Then we multiply these two together and double it. So 2 square root of y. Then we square the last one. And then we factored out the pi, so this is just -1. And it's kind of nice. The plus 1 and the -1 will cancel out. That's good. So we squared this binomial. And now this is from 0 to 4. It's dy. So this is power rule. Sorry, guys. This is going to be crowded. Maybe I should just move over to like a blank page. I'll do that here. This is power rule. The integral of y is 1/2 y squared. Raise the power by 1, divide by 2. This is power also. Square root of y is y to the 1/2 power. So we're going to raise the power by 1. So add 2 halves. So it's going to be y to the 3/2 power. And we need to divide by the new power. So 2/3. And we're doing this from, and I guess pi is multiplied on the outside here. And we're doing it from 0 to 4. So when we plug in 4 here, it's pi times 1/2 of y squared. 4 squared is 16. Half of that is 8. Here, okay, this is square root of y cubed. And so when we plug in 4, square root of 4 is 2. 2 cubed is 8. And it's 8 times 2/3, so 16/3. And when we plug in 0, we'll get 0. So let's combine this into a single fraction just so it looks a little bit nicer. This is 24/3. 8 is 24 divided by 3 plus 16/3. I'm just making these both have a denominator of 3. So this is 40/3. And so 40/3 pi is our volume of revolving it around. So this takes a little while to get used to, but again, the big idea is we need to find a formula for the area at each y, which will usually involve, you'll need to find what x is equal to by switching around the formula to find what x is equal to. And you'll go from the bottom y value to the top y value. So let's see how you guys can do on your own here. This is a no calculator problem. Now guys, these are old AP free response problems. Not everything will be, going around the y-axis and stuff like that. So, don't start thinking everything is going to be this type of problem now. Most problems are normal, just like before. So let's look at this. Find the area of R. Go ahead and do that on your own. And guys, the area of R, we can just do like we've always done before by going like this. This is the integral from 0 to 2, right? This is at 2, 4. So that's the intersection, the integral from 0 to 2 of the top one. It's the linear one, so it's going to be 2x is the top one, minus the bottom one, that's the curved one, that's x squared, dx. And let's do this. So this is the antiderivative. It's going to be x squared minus 1/3 x cubed. We are just doing power rule here from 0 to 2. Plug this in, we get 4 minus 8/3. And then when we plug in 0, that's just 0. So 4 minus 8/3, I'm just plugging in x equals 2. And 4 is in thirds, this is 12/3. So 12/3 minus 8/3 is 4/3. So 4/3. So hopefully we got that, but I want to show you guys, it is possible. It's not advised. I'm not saying you should do this, but it is possible to also find areas by going up the y-axis as well. Instead of adding up these heights, which is top minus bottom, we can add up these heights, which is the right x minus the left x. For both of these, you'll need to solve for what the x is. So here to solve for x, we divide by 2, so x equals 1/2 y. Here to solve for x, we take the square root of both sides, so x equals square root of y. And this is, the linear one is going to be the one on the left, and this is the one on the right. And so another way to do this integral is the integral from, and I'm going to say, so it's the right x minus the left x. So the right x is square root of y minus 1/2 y dy. What do the limits need to go from here? Well, if we're adding up these and we need a formula for the lengths at each y, we're going along the y-axis. So we need to go from bottom to top. So it goes from 0 to 4. Notice on this one, it went from 0 to 2 because that's what the x's did. X went from 0 to 2, but the y's are going from 0 to 4. And this will come out exactly the same way. You'll notice, it looks a little bit different, but it will come out to be exactly the same answer. Feel free to do it on your own and verify that it comes out to be 4/3. It would. Again, there's no reason not to do this way. If it works going along the x-axis, then just do that. It's easier. But if it doesn't, you can do the y-axis. It's fine. You'd get the same answer. You'd get full credit. It's all great. Okay, the region R is the base of a solid. For this solid, at each x, the cross-section perpendicular to the x-axis. We have to be careful here because if it had been y-axis, that would change what we were doing. We now need to pay attention to that. Perpendicular to the x-axis has an area of sine of pi over 2x. Find the volume of the solid. Go ahead and try that on your own. So it tells us the formula for the area at each x. So it's literally just the integral from 0 to 2 of a of x, which is the integral from 0 to 2 of sine of pi over 2x. So we don't have to calculate an area. It just gives us the area at each x. That's nice. And this we can do this integral using u substitution. Here, there's like obviously something inside of sine. U is pi over 2x. This is just a constant. And so the derivative is pi over 2. And so we need to divide by pi over 2. So this is dividing by pi over 2 is 2 over pi, the integral of sine of u du, right? So we changed it to u's, and I divided by the du to undo the chain rule. So instead of multiplying by pi over 2, we divide by pi over 2. And so the integral of sine of u is going to be negative cosine of u, because the derivative of cosine is negative sine, from, well, okay, so hold on. Where was this 2 over pi? I guess that should be here. So we need the negative in front. And I'm going to go back to x's, I think. So this was cosine of pi over 2x. And that way I can just keep it from 0 to 2. So let's do this. So when we plug in 2, I'm going to factor out the negative 2 over pi, because it'll multiply times both of these. So when I plug in 2 times pi over 2, it's just cosine of pi, minus, when I plug in 0, I'll get cosine of 0. And you can leave it like this, guys. This will get you full credit on the AP exam because you don't need to simplify. But I'm going to simplify. Cosine of pi is negative 1. That's what the x value is there. And cosine of 0 is 1. So we get negative 1 minus 1, which is negative 2. So we get negative 2 over pi times negative 2. These multiply together to make a positive. Negative times a negative is a positive. It's 4 over pi. So that is the volume. And you had to use u substitution there, guys. The u substitution stuff isn't going away. Last, C, and I'll change color here to make it a little bit easier to read. I was trying to stick to one page, guys, but we really could have used a little bit more room on this document. Another solid has the same base r, okay? For this solid, the cross-section is perpendicular to the y-axis. Be careful. The cross-sections perpendicular to the y-axis are squares. Right, but do not evaluate. So we don't need to find this. This was on the no calculator section. An integral expression for the volume of the solid. So we've got squares sticking up. And it's really, really hard to figure out what on earth the area would be at each x. But it's really easy to figure out what the area is at each y because they're squares. So we're going to need to do the integral of the area at each y. And this area at each y is going to be a square. Now, if we're going along the y-axis, what we should get is the integral from 0 to 4, because we have to go do bottom y, or up to top y. So bottom to top instead of left to right. So the integral from 0 to 4 of a of y, and what a of y is equal to is this length squared. So, because a square is going to have whatever this distance is times itself. So this distance is this x value minus this x value. We already earlier solved for x, but we might not have done that earlier, if we were just solving this problem normally, in which case we'd need to do it now. So we need to find the x on the left is 1/2 y. The x on the right is square root of y. Again, that's found by just solving for x from these ones. And so the right minus the left, so square root of y minus 1/2 y is this distance. And that distance is being squared to find the area of a square. So if this distance is, square root of y minus 1/2 y, then the area of a square is going to be this distance times itself, because it's this length times this length. So hopefully we feel, oh, you guys couldn't see this. It's this length times this length. So it's squared. It's the same thing on both sides because it's a square. So this is good enough to earn full points because I have to find what a of y is, but the normal way to write it would be the integral from 0 to 4 of square root of y minus 1/2 y squared. Hopefully we feel okay about that. All right, last one, guys. Let's see if we can do this on our own. Here's r. This is a calculator allowed. Here's r. It's natural log of x and x minus 2. Confirm in your head that you know which one is going to be which. Hopefully we know that natural log of x is going to be here with this asymptote, and x minus 2 is the linear one. It's the straight one. Find the area of r. Okay, so the area of r is going to be the integral from Okay, we need to find these intersections. So let's, in our calculator, put, oh no, y equals natural log of x. That's the top one, so I'll put that one in. And in the bottom one, we've got x minus 2. And I guess I should change my window so I can actually see this. Let's go the y-min, let's set to -5. And that's going to be good enough to see. So there's that area. So the intersections are, I'm going to write this here. I'm going to write this to the side. There's an intersection at 3.14, almost looks like pi, but it's not. 3.146, comma, 1.146. And there's an intersection, the other intersection. So I wrote down both the x value and the y value here. The other intersection is enter, enter. When we get to guess, we need to press over to the left until it's closer to this one. And press enter again. And the intersection is 0.1586, whatever, comma, -1.841. So these are the intersections. And so it's fine to say it's the intersection from the x on the left, which is 0.1585. I went to 4 decimal places here because it was, or 86, because the next one was a 5, and I was worried it would, like the rounding would throw it off. It probably wouldn't though. To 3.146 of the top curve minus the bottom curve. This is our area from the first day. So it's natural log of x minus x minus 2. Make sure that's in parentheses, dx. And so let's do that. And math, the integral from 0.1586 to 3.1146 of natural log of x minus x minus 2 dx. You know, I probably should have done, it probably would have been better if I just done y1 minus y2. Let's just show that that comes out to be the same thing. So vars y1, variables, we press the variables button, of course, to get there. Vars y2 dx. Okay, so that area is 1.949. Now, find the volume. Notice we actually could have done the integral going up the y-axis by saying it's the integral from, this is also equal to the integral from the bottom y, -1.841, to the top y, 1.146, of the x on the right minus the x on the left. So I could have also gone this way, right? And for that, I would have needed to solve for x. So to solve for x here, I would do e to the power of both sides. So x equals e to the y, e to the natural log of x would cancel out. And here I would need to add 2. So x equals add 2, y plus 2. And so if I did the integral of the one on the right minus the one on the left, so y plus 2 minus e to the y from bottom to top, this, and you can verify this in your calculator, you just put in x's instead of y's, this will come out to be the exact same area as this. They're both ways of doing it. But I mean, like, I 100% would have done it this way. Find the volume when this is rotated around the line y equals -3. So y equals -3. It's going to be down here somewhere. Here's y equals -3. And go ahead and find this on your own. Hopefully we notice this is one of those ones where there's a blank space in between. This is like a little radius minus a big radius one, or a big radius minus a little radius one. So in B, we've got, can you guys see that? Yeah, you guys could. Okay, so pi times, oh, it's the integral from, and this has to, guys, this has to be along the x-axis. It has to go from 0.1586 to 3.146 of pi big R squared minus pi little r squared. Of course, we can factor out the pi there too if we wanted. And big R is the distance from the center of rotation to the top function. So top y, which is natural log of x, minus bottom y, and the bottom y is -3, y equals -3. So I guess we could put natural log of x plus 3. And the little r is going to be from bottom, from where the blank spot ends to the center of rotation, so top y minus bottom y. And the top y is y plus x minus 2, y minus 2, sorry, x, yikes, x minus 2 minus negative 3, which is, so I guess that's equal to x plus 1. Minus negative 3 is plus 3, negative 2 plus 3 is 1. And so, again, I could leave it like this, or if I wanted to, I could put the integral, and I'm going to take the pi to the outside, of natural log of x plus 3 squared, that's r squared, right, minus x plus 1 squared. And this is a calculator problem, so I'm just putting it in the calculator. So, okay, so here it is. This is y1 plus 3 squared minus, oh no, I lost my thing. I was trying to not have to type it again. I was trying to insert, but I messed up. y2 plus 1, oh no, it's y2 plus 3 squared. I could have typed in natural log of x plus 3 and x plus 1. That would have been fine. And I need to factor out the pi. I guess I forgot to bring the pi to the outside. So I'm going to press second insert to put a pi there. Okay, so this should be it. So this is 34.199. If I had put 34.198, I'd get full credit as well. All right, the last one. Try to do it on your own. Write, but do not evaluate, an integral expression that can be used to find the volume generated if r is rotated around the y-axis. So here's the y-axis, and we're revolving r around the y-axis. So what would the equation be that would get me, or the expression be, that would find the volume? So the volume is going to be the integral from, if we're going along the y-axis, it has to go from bottom to top. So it's going to be the bottom y to the top y. Now notice, if you hadn't done that in part A, if you hadn't written them down, you would just like find the intersection again and find what the y value was of this one and find the y value of this one, and that would be the top minus the bottom. So negative 1.841 to 1.146, bottom y to top y, okay, of, what is it? It's being rotated around, and so we need to do a big radius. There's a blank circle here too, right? Like there's this blank circle here. So this is going to be pi times big R squared minus pi times little r squared. And big R is going to equal here to here. So it's the right x minus the left x. The left x is 0. The right x, I need to solve for x here. So if y equals x minus 2, then x equals y plus 2. So x plus 2, that's on the right, minus 0. So it's just x plus 2. So that's big R. Little r is equal to the distance from here to here. So this x minus this x. Now I need to solve for this x. X equals, so again, if y equals natural log of x, then I can do e to the power of both sides to cancel that out to get x equals e to the y. So x equals e to the y. So this radius is going to be e to the y minus 0. So the right x minus the left x, which is just e to the y. And guys, this is good enough to earn full credit because it said write but do not evaluate. And I've said what r is and I've said what e is, and this will get full credit here. So that's it, guys. Again, the big idea is sometimes, like if you do rotations around a vertical line instead of a horizontal line, if you do a rotation around a vertical line, it'll make circles going along the y-axis. Or if they tell you there's an area perpendicular to the y-axis. So the keywords here, let me go back to our top here. Areas and volumes along the y-axis, the main times we're going to do it is when it's perpendicular to, like you end up with an easy area perpendicular to the y-axis. So, you know, you're adding up areas or volumes or lengths that are perpendicular to the y-axis. Every once in a while there's an area one where you want to do it, and let me just tell you what's going to make that happen. Let's say you have some region, and do you remember in our warm-up problem where they said the vertical line divides it this way? Well, sometimes they'll say, you know, there'll be like some region and they'll say the horizontal line divides it into 2 halves. And then it's really much easier to say, look, the integral from right to left, from like here to here, is equal to the integral from right to left from here to here. Like, that is so much easier than trying to, like, you could do, there are other ways to do it. You could find like this area, like multiple like areas of different places. Like, you can do different regions and make it work. But it can be nice to go along the y-axis for areas if there's like a horizontal line, splitting it into like 2 sections or something like that. So guys, that's it. This is not a huge topic. If you were a little bit confused on this y-axis stuff, it is way less common on the AP exam than stuff going along the x-axis, but it comes up. Like, I would imagine there'll be a question or 2 maybe on your AP exam this year that is going along the y-axis, but most of the stuff that's areas will be going along the x-axis. So we're done learning areas and volumes. We have a test coming up. After that test, we'll be on our last unit of the year, differential equations. So we're almost done with the year, guys. So work hard for these next little bits, and then we'll be ready. We'll be done.